Good afternoon. I'm here today to talk about a paper that I co-authored with Lieutenant Colonel John Alt. It's titled Bayesian Networks for the Human Element. So we'll be talking about two things: Bayesian networks and how we can use them as models to represent aspects of the human element in military operations. I'll focus a lot of my talk on the first part, and in the paper you'll be able to delve deeper into the second part. So I want to take you through the paper, but first let's talk about what we're doing here. There. Speed ahead. So it happens this paper won the Military Operations Research Society John K. Walker Jr. Award in 2010. John and I wrote it in 2009. We've been working on Bayesian networks for several years as components to model. And what I'm going to do is take you through the background of how we came to write the paper, walk through the outline of the paper, explain what's in it, and then give you a simple example that illustrates some of the major points that are part of the paper. So John and I had been doing research trying to represent civilian populations in stability operations. The military conducts stability operations as a component of all military operations, and that's the part of our operations that focus on the civilian population rather than on our adversary and our allies and our own operations. So we have offensive operations, defensive operations, and stability operations that are the three components of a military operation. In Iraq and Afghanistan, obviously, stability operations, irregular warfare, counterinsurgency, counterterrorism, those were the main focus areas that we were involved in. But even before that, John and I had been doing work representing military decision-making, cognition, how soldiers, both our soldiers, our coalition soldiers, our adversaries made decisions. And in both cases, whether we're looking at civilian populations or whether we're looking at that human element of decision making, we found that there were useful ways that we could use Bayesian networks to represent those phenomena. So our whole intent is to build models that represent phenomenology, and these models are models of decision making or models of behavior and attitudes that occur within uncertainty. So we don't know for sure exactly what the state of the world is, and the state of some of the variables that influence what we actually observe. Bayesian networks are excellent tools for exactly that purpose. So I'm going to take you through the paper outline. Here it is. You can see the parts of the paper, and I'll explain the main points from each of them. So why Bayesian networks? So I've already touched on this. Bayesian networks are a representation of our knowledge about some particular phenomena. That knowledge can come from theories that we develop from social science. It can come from actually observed data. But in either case, they're models that use random variables. So, for example, a random variable might be whether it will rain or not on a given day. So, in that case, the answer is yes or no. It's a categorical variable. And in particular, Bayesian networks let us relate these variables together. Bayes' rule comes into play when we're talking about the relationship between random variables. So we observed that Bayesian networks were useful for representing phenomenology in military environments, especially related to that human element, human decision-making, human attitudes. It might be how someone's going to vote, whether they're going to support the insurgency or not, whether they're going to comply with government policies and those types of things in that type of environment. In a military environment, it might be whether a commander is going to attack or not. But whatever sort of decision we want to model, and these can be modeled for a variety of purposes, but it's about understanding and supporting decision making. So the rest of the introduction just lays out what I'm going to be explaining to you, what the paper contains. So Bayesian networks. It's a network because it consists of nodes and arcs. The nodes each represent a random variable. The arcs represent a relationship among random variables. And they're based on Bayes' rule. And Bayes' rule relates conditional probabilities to marginal probabilities. The probability it rains today is a marginal probability. The probability it rains today, given it rained yesterday, is a conditional probability. We're conditioning on whether or not it rained yesterday. And that changes the distribution of probability for whether it rains today. If we have information like whether it rained yesterday, that allows us to make a more precise, although not a very good estimate about whether it will rain today. But Bayesian networks can scale up to hundreds of variables. So you might look at all the possible data that you have and determine which variables are most critical for helping you to infer or predict something. The next section is about machine learning. And it's here because it's great to be able to draw this arc and node network and look at these variables. But unless you can apply data to it and actually do computation, then the value is somewhat limited. Machine learning is a method from computational statistics and artificial intelligence that allows us to build computational Bayesian nets. This section deals with some of the ins and outs of that and provides some references. Then there's a section that's about Bayesian reasoning. And it's here because Bayesian networks and Bayesian methods are not without controversy and not without challenges when we come to the need to try to implement them and to use them and to interpret them. So we want to confront head-on the detractors for the use of Bayesian reasoning and Bayesian methods. And we want to make that case that there are merits in Bayesian networks that make them a better tool than many other methods for some specific types of representations and modeling we want to do. Then we step back from having talked about that computational aspect of Bayesian networks and about the controversy and challenges with representing human decision making, representing populations and their attitudes and those types of things that we say we can do to some extent with Bayesian networks. We want to talk about why it's important that we have this visual representation of the model. We have these arcs and nodes. And the reason is that humans can read and understand those. And we can take a theory or we can take a hypothesis and we can represent it with that conceptual model. Even if we don't know how to compute on it yet, we can begin to represent it. Conceptual models are incredibly important because they cause us to have an opportunity to debate the merits of the model and to focus in on what variables we agree might be relevant. And of course, in that Bayesian network, those arcs that connect nodes imply something about how we're thinking about that model. We're actually, in all statistical models, we have some underlying theory that's being embodied by them. We often fall into the trap of not making that explicit. With Bayesian networks, if you know how to read and interpret them, it's not possible to hide that model because it's a complete model on the entire probability space. You specified all the nodes. You decided what state space that you're concerned about with each of those nodes that represents a variable. Then we go into two specific examples that I've already talked about. That's modeling what we now call mission command. At that time we called battle command. And that's about our own decision making and decision makings of adversaries and things like that. We can borrow theories from cognitive science as well as use empirical studies or survey data or other things to build these models. And this section details one of those models. It's a naturalistic decision making model that comes from cognitive science. It's about how people make decisions in time-sensitive, high-stakes sorts of environments. You know, someone who's commanding the scene where a team of firefighters is fighting a fire. That was the genesis of this particular model. And it shows a military example of it. The next section deals with that representation of the human population. And it presents an example that's a theory of planned behavior that's about how people make decisions about the things that they do repetitively and what influences and changes their behavior in those things. It comes out of the medical science. And then finally, the paper's conclusion, which wraps it up, solidifies the case, and points to the references for further reading. So now I've told you what the paper contains and how John and I came about to write it because of our experiences over the prior years working with Bayesian networks. I want to give you a simple example so you have something that's, that you may have some background with. So in genetics, Mendel did experiments with pea plants. In his experiments, he demonstrated the idea that some alleles are recessive, some are dominant, that you can have visual characteristics, but the underlying genetics can be a little bit more complex. So the simplest example, you have something like the color of the flower. And it's red if you have two dominant alleles, or one dominant and one recessive, and it's white otherwise. So this represents that. You have the genetics of the plant, you have the color of the plant. Now we can only see the color. We infer the genetics from the theory and from other things. But in this example, computationally, if the plant's white, then 100% of the time it has two recessive genes. In this case, if the plant's red, 2/3 of the time it has one dominant, one recessive. 1/3 of the time it has recessive. That's the example of computing on the Bayesian network, based on the theory. Of course, it's only interesting when they get together and they have sex. In this case, we have the child. And what when we read this is, of course, the color depends on the underlying genetics, and we observe that. But the genetics of the child depends on the genetics of the parent. So you can think of a population here, and it's distributed in this manner, and we see 3/4 red and 1/4 white, and that remains stable generation after generation after generation. Of course, if we observed a particular color here, like red and white, that would change the distribution here. And if we looked at the child, the offspring, it was red, that would tell us things about its parents, and about its own genetics and the likelihood that things are distributed. So to summarize the main points, Bayesian networks are valuable for representing the human element in military operations. They're simple, they're transparent, they're traceable, and the paper describes these aspects of Bayesian networks. What are your questions? Thank you.